Welcome to Hot Chips 26. Session 6, High Performance ASICs.
All right, we're going to start this session here. So my name is Michael Taylor. I'm a professor at UC San Diego. I'm the session chair. This session is going to be about high-performance ASICs. And this is near and dear to my heart. I think that we have some really exciting ASICs that are being presented today, and FPGA-based system as well. I think ASICs are always pretty interesting because they're often targeting new application domains, and I think we'll definitely get a good flavor of that. Our first speaker is Raphael Polig. His talk is entitled Hardware Accelerated Text Analytics. He's a PhD student at IBM Research in Zurich. His research interests are in hardware acceleration of text analysis, and he has a master's in EE from TU Munich.
Thank you, Professor Taylor, for the introduction, and thank you for having us here and me for presenting the Hardware Accelerated Text Analytics project that we're having at IBM Research at the moment. It is a joint research project between the research lab in Zurich and the research lab here in Almaden in California, who wrote the original text analysis software. And there's also been support from the colleagues from IBM Research in Austin. So let's see what the next 20 minutes have in store for us. I'll first give you an introduction, what text analysis is and what it is used for, and why we want to accelerate that. Then I'll introduce you to System T, which is the text analysis software that is used at IBM. I'll then introduce the hardware acceleration flow that we have attached to it, and I conclude with some experiments and results that we have produced. But first, what is text analysis, or text analytics? It is a part of information extraction that deals with unstructured or semi-structured text data, and it transforms or extracts the information from that data into a tabular data format or information set. So in this example here, a little bit old, but quite famous, I'm interested in finding names of people, what organization they work for, and what is their title that they hold within the company. So that is usually done in 2 steps. So the first step would be that I would like to find all the entities and attributes within the text. That boils down to that I find certain categories of words within the text, such as CEO, VP, and founder, which I know are names or words of titles that I'm looking for. So after the first step, I'm ending up with a text that is nicely annotated as the one in the figure. And in a second step now, I want to correlate these findings or correlate the attributes to the entities that I find in the text. So that would be, I'm looking for close distances, such as that the word CEO is next to the name Bill Gates, so I can assume that Bill Gates is a CEO. This is the simplistic way of looking at it. Certainly there are more complex queries that you can write that take into account the end of a sentence or certain negating words that then might say it's right the opposite way. So what are we really using it for then, other than such nice examples? We all know that we're living in the world of big data, and it is big text data. one part of it is big text data. And big data would be happening right here in the audience, where people are writing articles, are posting comments on Facebook, write some Twitter tweets, and I could use text analytics to find out what you think about my talk right now. But really, what business people would do, they would be interested in what you think about their products. So, and there's quite a lot of data that can be searched for when we think of having 400 million tweets every day on average. Marketeers would be very interested to know what you say about their products. Other application domains are more in the medical space, where medical companies are searching scientific publications to find out the interplay between two different substances and what has been studied already, so that they don't have to repeat the costly experiments themselves. Or maybe law firms want to check the patent databases for a case that they're preparing or a disclosure that they're preparing. And that was the task for the University of Sheffield, that has a software called GATE, a general architecture for text engineering. It's an open source Java software that you can use for text analytics, and it's quite famous, so the scientific publication of it is cited more than over 1,000 times. And they were, in 2008, they were quite proud that they could sustain 200 kilobytes per second text throughput and analyze that. In other words, it took them 6 days to analyze 100 gig of data and patent data from the USPTO database. Now, that database is multiple terabytes large, and it's growing every year. So you need to do that at a faster rate. And there's certainly other applications that even want to search more and larger data, and data that is growing even faster than that. So CPUs seem to be inefficient at executing these queries because it ends up having regular expressions. You need to do backtracking in these applications, so you won't be able to do it very fast on CPUs. So what's one way to get out of that? We're also in the world of cloud now. So everything that you can do on a single node with this, with the query, you can distribute that into the cloud, and every node in the cloud would then work on a separate set of documents to produce the results, and then you collect them back together. So that's what they did. A couple of years later, they introduced Gate Cloud. So they built a nice framework around their Gate framework, and now you could deploy it into the cloud. Obviously, the speed now, or the throughput increased by how much you want, because you can deploy it on as many nodes as you like. But what was interesting here was that the CPU time nearly doubled always from the server deployment to the cloud deployment. So also that seems to be an indication that it is not the most efficient way of doing it. On the other hand, or another application that came up in this time was query compilation. So that people would compile a query to an FPGA, and the FPGA would maybe pre-filter certain data that you would read in from a disk or from a network stream. So a quite famous application of that was in the Netezza fast engine and the appliance for a database. And that was so efficient that IBM bought them. But the drawback here is that we couldn't use this query compilation right out of the box for text analytics, because it is it's missing the essential features of regular expression matching and dictionary matching that we need here. So at IBM, we use a text analytics software called System T. It introduces a query language called AQL. It is a rule-based language and has a similar syntax to SQL that we know from databases. And that gets then fed into the system T optimizer that will compile the query graph, compile the query into an operator graph, which then can be executed by the system T runtime. So that gave them the opportunity, using this optimizer, to really find an optimized execution plan for the software on the CPU, and they saw some nice throughput gains here. So let me show you an example on how an AOG looks like. So I'll spare you giving a tutorial on AQL, but the operator graph is quite interesting. So on the very top, I have my input text, and I would like to find out who I'm going to meet tomorrow. And usually the first line of operators in such a graph is the extraction operators. So these would be regular expressions I would like to find in the text, or certain strings that I would like to find within the text. These operators produce small tables that contain spans. A span would be a tuple of two integer values that tell me where the word starts and where it ends within the text. And then afterwards, I'm using relational algebra operators to correlate these spans that I have found earlier with the extraction operators. So that I'm trying to find that Mark is placed next to Scott and Howard, for example, is placed next to Smith. But in real life, these examples or these queries get a little bit larger than just 9 operators as we saw before. They can have multiple hundreds of operators. They can have multiple outputs also on the bottom. But they all start always from one single node, which is, in this case here, it's always the document that you're searching for or that you're scanning through. A good thing here is, though, that there are no loops within these query graphs, so there's no need to unroll them, for example. But the operators themselves are quite complex. So how do we accelerate such a system, or system T in this case? The acceleration concept is that we're looking for a subgraph within the operator graph that we would like to offload onto the FPGA. So we partition the operator graph into hardware graphs and a software graph, and we replace this subgraph with a subgraph operator, which we then can hand back to the software side, and we compile the hardware part to the hardware. And we all do that under the aspect of maximizing the throughput of the overall system. So here on top, you can see the original system T compilation flow and execution flow. But in this case now, we take the operator graph, how it is coming out of the optimizer, and attach our acceleration framework on the very bottom. So as I said, we're performing a partitioning step, which is now finding out what subgraph do we want to take out of the overall graph. And we end up having a software supergraph and a set of hardware subgraphs that we want to compile onto the FPGA. Then a second important part of our compiler is the compiler that is generating Verilog code out of these hardware subgraphs. So this compiler really is a set of compilers that will generate regular expression architectures. It will produce modules for the various relational algebra operators, and then these will be stitched together by the top-level compiler in such a way that they can operate in a streaming fashion so that the extraction operators are never blocked by any of the relational algebra operators on the lower part. The compiler also generates the interface to the software, because this looks always different. There might be a different number of buffers being generated. The buffers might have different aspect ratios, so this needs to be generated for each query individually. I'm an honest guy, and there is a dashed line going back to the system T runtime. So the automatic readback of the supergraph is currently not working yet, but we have a set of supergraphs that can exercise the query that we are running then on the right-hand side. So what's the deployment system look like? We were working with a Power 7 system and a card that was built in the Austin lab that is attached to the GX bus. It is a system that was a predecessor system or used to study copy, which we now know that is deployed within P8. This system here uses a software-based MMU. That means that within your application you have a translation server running that would translate virtual addresses that you're accessing from the FPGA into real addresses that you can then access on memory. So, what that gives us, though, the virtual addressing, is that we are getting rid of all the copying data into a pinned memory area, and we can access the whole system memory as it is used or accessible by the Power 7. So when the query runs on the Power 7, it also takes as input the document buffer, and the FPGA on the other side can access that very same data, and it can write back into the result buffers that the software knows where they are. And so without having a driver in between that is then copying these buffers back to software, the software can just continue to run without interference. In a complete way, since System T is also a Java software, we have to get out of Java first before sending it off to the FPGA. So there are multiple threads running in Java and would be submitting documents. And as I said, there is this communication thread or translation server running all the time. And as the software-based MMU is introducing quite some latency, the setup of such a transfer is a little bit costly. So we decided to introduce some coalescing within this communication thread so that multiple documents would be grouped together before being sent off to the FPGA. And when the FPGA is finished, it would send the information back. It's already demuxed into the correct buffers. It was just signaled the thread that your results are ready, and then these threads could continue to run. So let's have a look at some of the experiments and results we see. So these are software results when running System T on a 2-socket Power 7 system. You can see the throughput on the right-hand side, and on the left-hand side you see the relative execution time of the operator categories that you have within the queries that we were using. So you see that the queries T1 to T4 are all mainly dominated by regular expression matching and dictionaries, whereas the T5 is dominated by relational algebra operators. That also reflects a little bit in the throughput numbers that T5 is quite a bit faster than the other ones, but still throughput is limited at around 15 megabyte per second at a maximum that we see there from purely software. So now when exercising the system using the FPGA, we had the FPGA configured to have 4 operator graph pipelines, each running at 250 megahertz, but each of these pipelines was able to have a throughput of 125 megabytes per second, so we have a total of 500 megabytes per second throughput in there. But you also need to have the interface and the software fast enough to really fill up the bandwidth that the FPGA could use. So what you can see here is the number of software threads on the x-axis and the actual throughput that this whole system would get using the number of threads. And so what we saw was, even though we were using this coalescing mechanism with small documents of 128 bytes or 256 bytes, we were not able to get the full throughput of the system in this case, but only with larger documents of 2K and some 20-ish software threads, the software was able to fully exercise the accelerator in this case. So we were then estimating the throughput for these queries that we were seeing before for various scenarios. So in blue, you can see the original software throughput running with 64 threads on the power 7. And then in red, you see the speed up gain that you can get by only offloading the extraction operators onto the FPGA, and the remainder of the relational algebra is done in software. The green bar shows you the speed up that you can get by having one single convex subgraph being compiled to the FPGA. That means all the relational algebra operators that follow the extraction operators and don't require any software input are compiled to the FPGA. And then in yellow, when we would compile everything that we have or that we support onto the FPGA. And so we see we can get speedups from around 2.5 for small document sizes to up to 16 times for larger documents and the queries that are friendly to our accelerator in this case. So what's next for us? We would like to move, or we are moving on to Power 8, and I would have loved to share some results with you already, but we're not there yet at that point. But what we would assume to see is, on the one side, we see higher software performance as Power 8 is improving on that. We now really have a copy coherent system. So the accelerator is attached in a coherent way. So we get rid of this software MMU stack that we have there. And now we also can use multiple cards on the Power 8 to accelerate maybe larger queries even then. So all I have for now is software measurements on the Power 8 system we've received so far. And what we can see that is all for the T1, T2, and T5 queries, there is a per thread improvement of about 60% already. And knowing that Power 8 has more threads available on chip, you can get up to a 3 times improvement for the whole system here. So, but even then, we're around 20 to 25 megabyte per second maybe. So that is still good for our accelerator, since we're in the 500 megabyte range. So P8 can benefit from having such an accelerator within the system. So, and that concludes my talk.
Okay, great. We have some time for questions. I'll start with the. Oh, we have a question here already.
Yeah.
Go ahead.
Yeah, John Massey from TechVisor. So talk some more about the MMU and maybe cache coherency and operating system interactions. How, is there in effect an MMU over on this board, and how does that get synchronized with the other MMUs, and to what extent did the OS have to know about this, and was there cache coherency? I mean, this has basically been a problem in wanting to use FPGAs for a long time, of getting the virtual addresses.
Yeah, so you mean on the P7 system that I showed, or on the new copy system?
On the new one, since you opened that topic up.
I really don't, I haven't worked too long on the copy system so far, so maybe I can't comment on that, Kurt.
Okay. Well, I mean, again, that particular issue has been a challenge for a long time in getting good use of the FPGAs in a computer system.
Yeah. So all I know now, it is a cache coherent system.
Okay.
So it's using the same mechanism as a CPU core is. Yeah.
Okay. Great. Thanks.
Mo Hagigat Intel. So do you know if the in the base studies that found CPUs slow in regular expression parsing, were they using SIMD instructions at all or not?
I don't think so, that they were using SIMD instructions. I know of studies that were using SIMD instructions or special instructions to optimize a regular expression matching in this case, or also the tokenization process of text analytics. But still, that wasn't getting that throughput that we're seeing now with the FPGA. Since you have so many regular expressions and dictionaries you're looking for, you're profiting from the high parallelism that you can gain on the FPGA.
Right, right. But then combining parallelism of CPUs and SIMD.
Sure. Yeah.
I mean, in JavaScript, I know for sure that all browsers have specialized handling of regular expression. They are all using SIMD instructions.
Okay.
Thank you.
Manuel Saldaña, Huawei Technologies. I'm just curious, I mean, sort of like a follow-up on the first question. You have the MMU, the translation between physical and virtual addresses, but then on top of that, you have the JVM, which adds yet another layer of complexity to that. So just wondering, why did you choose Java in the first place? And wouldn't a language closer to Metal like C would give you better performance just using that instead of Java?
So System T was there before our acceleration project was there. So we were starting from something that was already a product at IBM and then tried to accelerate that. So the software was already written in Java, and we didn't want to write it up from scratch, right?
Okay, I have one more question. We saw earlier in a talk that they were looking at adding FPGAs to Bing to do better, search, which I guess would be some kind of text analytics, probably maybe not as hardcore as what you guys are doing. If you look at the acceleration you did, what would be your wish list for what you would add to an FPGA to do text analytics better? Does anything come to mind?
No, nothing really yet.
That's quite okay.
We're actually quite happy with the FPGA architecture so far. Maybe the only thing, since we were using an IP block from an earlier project that is working on using the block RAM, and using that in a single cycle is quite challenging. So if that would be one wish list, that the internal memories would be even faster in a single cycle access, that'd be great.
Great. Okay. Thank you. All right, let's thank our speaker. So our next speaker is David Moloney, and his talk is entitled Myriad 2, Eye of the Computational-Vision Storm. David worked on a variety of senior technical roles at Infineon, ST, and CEVA before co-founding Movidius in 2005. David holds a PhD in HPC on FPGAs from Trinity College, Dublin.
Good morning, ladies and gentlemen. First of all, I'd like to thank the committee for having us here today. It's a real privilege to be in front of a distinguished audience of peers. And I'd also like to thank the session chair, Michael, for useful feedback on the presentation. Today, we're going to present our next generation computer vision processing unit, or VPU, as we like to call it. Just to talk a bit more about the team, for those of you who aren't familiar with Movidius, we've been in existence for some time now. And I suppose our most important announcement to date was earlier this year. We were announced as part of Project Tango, as part of the vision processing subsystem. Project Tango is a new device class for mobile devices aimed at providing computer vision and visual awareness for mobile platforms. And essentially, based on our experience over several years working on computer vision projects, we've basically put that into this product that we're presenting today, Myriad 2. This is the work of a 70-person team. Only 5 of them are really hardware designers. The remaining people are all working on the software and tools. So there's a very important component there on the software and tools and the things that we'll get into later on in the presentation. Just to fill you in, first of all, in terms of the difficulties here, many of you may not be working in the computer vision area, and it's in an area of high flux. There's a lot of pressure to get better low-light images, to make thinner phones, and so on. So there's a lot happening on the front-end imaging system, and a lot of computational focus is now on moving from glass in terms of lenses into computation, and that's specifically in the area of multi-aperture cameras. There's also big change in terms of the actual 2D planar sensors themselves. Bayer CFAs have dominated for many years, and we're now moving to things like RGB NIR or RGB clear, where, for instance, you computationally reconstruct the green channel. And in fact, in many of the devices like Myriad or like Project Tango, you will find that there are more than one sensor attached. So you might have global shutter camera, regular VGA sensor, or regular high precision sensor, and let's say a depth sensor. And you need to basically take all of that data, collate it, extract feature points, extract metadata, and uplink that over a MEPI interface to an application processor that then runs Android and runs the Android HAL and basically does GPU rendering for things like VR. So essentially here you're talking about an area where it's very difficult to boil everything down to hardware. You essentially need a highly capable, flexible, software programmable platform to deal with the degree of change that there is in the front-end system. So as I said, we're moving from 2D image capture. We've moved from 2D image capture now to computational photography, where we're doing things like synthetically refocusing images to full-blown visual awareness applications, where we're trying to really emulate the human visual system, allow us to extract a 3D scene, extract wireframe, render that for VR and for more, let's say, commercial applications, things like trying to do interior design and so on. So there's a big swathe of new applications that are being enabled in mobile devices, so you'll be able to interact with the world around you in a more meaningful way without necessarily having to use the cloud to do that. So what's the rationale behind needing a special purpose vision processor? Well, the issue is that obviously ISP is a standard part of application processors. It's something that they do very well. But that pipeline is relatively fixed. It's aimed at high performance. When you start trying to do within the constraints of a mobile phone, where you have about 3 to 4 watts total that you can dissipate thermally in a handset, then you're left with about 1 to 1.5 watts to actually do the real work. And the fact is that these systems are already fairly constrained because they have to run Android, they have to do GPU rendering and so on, and adding computer vision tasks and even more complex tasks where you're using multiple sensors actually adds majorly to the degree of difficulty, and certainly it means that trying to stay within that 1 to 1.5 watt envelope is a massive challenge for any of the existing systems that are out there. So along comes Myriad 2, and really what we're trying to do here is provide a massive amount of compute on demand for these kind of vision processing systems that leaves the application processor free to do the jobs that it needs to do in terms of graphics and running the operating system. The 3 fundamental elements of the system here are the vector processors, of which we have 12, computational imaging hardware accelerators, of which we have around 20, and then the most important element to tie all of that together is the memory fabric that provides very high sustained performance capability from all of those hardware elements. And the system, as we've defined, and obviously then a whole series of interfaces like MIPI, USB, and gigabit Ethernet to talk to the outside world. The overall system is providing a nominal 600 megapixel per second throughput at 600 megahertz. And that is what allows you really to provide this level of vision processing in a very compact device. We'll get into a bit more detail now in terms of the individual components of the system. So as I mentioned, we have 12 vector processors. Each one of those vector processors is an 8-slot VLIW processor. And really here we've concentrated on a massive amount of parallelism rather than pushing the frequency. So we're operating at a relatively modest 600 megahertz in 28 nanometer, and we're concentrating on issuing a massive number of instructions in parallel across those 8 units. In the maximal configuration, it's equivalent to about 144 RISC equivalent instructions that you can issue in a single cycle. Obviously, depends on the application, but that's the maximum capability. And that's basically backed up by a 12-port vector register file and a 18-port integer register file that support the various functional units. And those 2 register files at 600 megahertz offer around about 200 gigabytes per second of memory bandwidth that allows you to get very high sustained performance. Within the processor then as well, we have 2 caches, 2 kilobyte iCache and a 1 kilobyte dcache that allow better locality for certain applications. And we have 2 64-bit ports to the shared multi-core memory fabric that we'll talk about later on. All of that and is backed up by a 256 kilobyte cache and a DDR controller that has a 64-bit up to 1066 megahertz interface to a stacked DDR die that we have in package. And that gives you, let's say, a data bandwidth of around 17 gigabytes per second maximally. That's available for vision processing on its own in an AP. You would have to contend with the other elements of the system for that. So the next element then is the hardware accelerators. And what we've done with the hardware accelerators is take the parallelism even further. Each of the elements that we've implemented as hardware accelerators, for instance, things like non-lumen denoise, luma filters, tone mapping and correction, histogram of gradients, etc. They've all been implemented as fully parallel system blocks that don't have any intermediate, or they don't have to go back and forth to memory. They're decoupled from the memory by line or tile buffers, so you can essentially fetch a tile, operate on it, and write back at an average throughput of 1 fully computed pixel per cycle. So this is not having to go back and forth to memory, gives you a massive saving in terms of memory bandwidth and power, obviously. So essentially, from a compute standpoint, we had a previous generation, Myriad 1, that was presented here in 2011. It ran at 180 megahertz at 8 of the Shaved processors, and what we did was basically to get 5x roughly just by scaling. We added 1.5 times the number of processors and roughly 3 times the frequency, so about 5x, and we had to add the hardware accelerators in order to get us to our target, which was to achieve about 20 to 30 times the amount of performance per watt for the complete system. And the system now delivers a total of around 2 teraflops FP16 in a 500 megapixel, or sorry, 600 megahertz clock frequency and 500 milliwatt power envelope. So just to provide a bit more detail here, the bottom of this diagram, we have the 12 Shaved processors. Each one of those has their own individual power island, because again, this is a system for mobile phones, and you need to have a lot of flexibility in terms of maximizing the standby power. Above that is the shared memory fabric. That shared memory fabric delivers about 307 gigabytes per second of memory bandwidth that can be shared flexibly among the hardware and software elements. As I mentioned already, the hardware elements are hardware coprocessors that are shown in orange above the memory subsystem are relatively decoupled from the memory subsystem, so you can very flexibly construct pipelines that consist of hardware and software elements using those hardware elements and then adding the special secret sauce for your particular application above those. Above that then we have 12 on the top right-hand or left-hand corner, we have 12 MIPI lanes which are configurable as either CSI, DSI inputs or outputs. That allows you to add up to 12 independent HD cameras to a single Myriad 2, and above that then we have a variety of other interfaces such as USB 3 and Gigabit Ethernet, as I mentioned before. On the right-hand side then we have a 32-bit RISC shown in orange, which runs the runtime for the imaging subsystem. And to the right of that then we have another RISC that's aimed at providing high-level OS support in terms of RTEMs or Linux for applications where you're operating standalone without an application processor in the picture. And below that then is the DRAM interface and the DRAM controller. So in terms of the die photo, we have these devices now back 2 weeks plus, and we're going to be starting to sample customers next week. And on the die there, you can see bottom left-hand side is the 64-bit DDR interface. To the right of that, then you have the Shave processors surrounding the 2 megabyte onboard memory array. And above that, you have the hardware accelerators. They're obviously all in close proximity to the memory in terms of getting high performance. Above then the memory on the top right-hand corner are the 12 MIPI interfaces, and to the left of that then is the USB PHY, the PLLs, and the SoC subsystem that contains the 2 RISCs and all the peripherals in terms of logic. And the first device that we'll be sampling now is a 28 nanometer HBM device, 6.5 by 6.5 millimeter FPGA package with 128 megabyte stacked DDR device in package. That's a 32-bit interface at 533 megahertz. So that's great. We have a huge amount of compute power. The question is really, how do you make that work for the customer? How do you make it possible to take applications that have been done in the lab, in MATLAB or in OpenCV, and get them working in a real application in a phone or a standalone device? And we put a huge amount of effort into tools here. In fact, of our 70-odd person company, 65 of them pretty much are working on, 60 of them are working on the tools, and that includes things like the compiler, Eclipse-based IDE, simulator debugger, etc., that we've developed in-house. We've then obviously developed our own boards in-house for the chips with a BSP, and on top of that, then we have different libraries. We have a computer vision library with hundreds of computer vision primitives, a complete ISP library that allows people, because obviously if you want to do computer vision, you have to do good ISP in order to make that work. We have linear algebra, and in fact, Tomasz, one of our interns, has 2 posters here about some of what we've been doing on linear algebra related to Myriad 1, but we'll be doing more and more of that for Myriad 2. And on top of that then, we mentioned we have a C and C++ compiler. On top of that, we've built OpenCL, and we built a graph API construction tool that allows us in Eclipse to describe a pipeline as a directed graph and basically generate all of the runtime configuration to make all the elements of the system work. So this means somebody can use pre-baked elements of hardware, software, add their own special sauce, and then without necessarily knowing all the ins and outs of the whole chip, be able to press the button and generate the configuration that's required to make all of this glue work together and deliver the user experience required. So in terms of applications, we have, for instance, a benchmark here at 30 frames per second depth extraction at less than 250 milliwatts. That's using about 50% of the onboard vector processors that we have, only 2 of the hardware filters, and a mix of 16 and 32-bit floating point data types. Another requirement for very low is for very low latency for VR applications. And Mike Abrash, one of the key technologists in Valve Software, talks about having to achieve less than 7 milliseconds for a fully immersive VR experience that doesn't give you motion sickness. And because we don't have a frame-based paradigm, we can operate on lines and tiles, means that we can achieve extremely low latency. And in fact, for 1080p video, we can basically calculate about 50K multi-scale classifications in less than 7 milliseconds. And this is the kind of thing that you can use to build, a very immersive Oculus Rift style gaming experience or other experience based on top of this chip together with an application processor, let's say in a GPU to do the rendering. So in conclusion, we've built what we, the man is regarded as the dog's best friend. Well, we've invented the application processor's best friend, something that takes a lot of the difficulty in making visual awareness and visual computing, takes it away from the AP and makes it possible to deliver this kind of functionality in a mobile form factor that's durable in terms of time and is manageable from a heat perspective. And it's our belief that you will see VPUs or vision processing units being to visual computing what GPUs are to graphics, very widely deployed in the industry in the coming years. So that concludes the talk. If you have any questions at this point, I'd be happy to take them.
We have some time for questions.
Manish Goyal from Samsung. Can you describe how many accelerators are for imaging versus vision?
I'd say it's around about 50-50. Obviously, many of those elements can be reused for vision applications. Let's say you can use polyphase up and down sampling in various different applications. You can use things like pyramidal Lucas-Canada optical flow in multiple applications. So they're very reusable components across both imaging and vision applications. And whatever we don't cover in hardware, which is a small subset that's very high performance, we cover in the software library, the MVCV library.
Do you support OpenVX?
We don't currently. That's certainly something that we're planning to do. But I would say that we've done the design with a view to being able to support OpenVX.
Thank you.
I think the gentleman just stolen my first question. So my second question is, you also contribute to the OpenVX standard, and how do you actually compare with other companies who also aimed at making computer vision specialized hardware? In your products, how do you compare with the others?
Do we contribute to the OpenVX standard? No, we're part of Kronos, and we've been attending the meetings, but we haven't been contributing to the standard. In terms of how we compare with other people, I mean, it's early days. We're going to be measuring. We've only got our silicon back a couple of weeks, and this is something that we're doing on our own and together with customers over the coming weeks.
Hi, Yasmina Vasiljevich from University of Toronto. Thank you for the wonderful talk. I just have a quick question. So you mentioned you have a DFG of kernels that essentially get mapped to the processors. And I'm just wondering if this mapping happens statically. Is it known at compile time exactly which kernel you're going to map to each processor? Or is it dynamic and determined during runtime?
Currently, it's static. I mean, a lot of these pipelines will be known. What you can do dynamically is have multiple configurations that you can load from an external source. So it would be nice to have a fully dynamic system, but I think right now, the static, we've determined that will do.
Great, thank you.
Dave, I'm Bob Stewart of Stewart Research Enterprises. Do you think it's possible to take a slur class optical zoom lens system and achieve something like infinite depth of field?
I'm not an imaging expert. I'm more of a hardware guy, but I'd say that's something that we work very closely on with domain partners in particular areas. I mean, with 70-person company, even if it seems quite a lot, when you've got to cover everything in terms of the tools and algorithms, it's pretty challenging. What you're describing sounds, even tougher to do, and certainly would be, something that we would work together with a partner on providing.
Thank you.
Hi, I'm Faison from Cadence Design Systems. So on your vector processors, you mentioned the frequency is 600 megahertz.
That's correct.
Which technology is this?
It's a 28 nanometer TSMC HBM process.
Is this the highest frequency, or is it just the frequency you're choosing?
It's the frequency for which we determine that beyond which you start to pay non-linearly in power terms for every megahertz in frequency. I mean, Michael was a student of Anand Agrawal's, and he had this curve that he showed where there's a kind of a sweet spot, and that was where we determined the sweet spot was around 600 megahertz. At that point, then you get the maximum throughput per milliwatt. So that was a design choice that we made.
Can you disclose the highest one that you can achieve?
We can achieve 800 megahertz, but you start to pay very high additional price for going to that higher rate. And right now, 600 megahertz is the design target for the device.
A second question is,
let's keep it to one question per person. Yeah, and we can recycle.
Holon from Huawei Technology. I just wanted to understand that CMX, the connection matrix on the chip, can you share some of the challenge to connect many hardware accelerators and the CPUs together?
Yeah, it's a difficult problem, both from a logic perspective and from a timing closure perspective. I mean, it probably makes more sense to have that discussion offline after here, because it's quite long. It'd be a very long-winded answer.
Okay, thank you.
Great. I had a question as well. So in your design, you have what I kind of view as being kind of a prototypical design for the future, which is you have vector processors that do kind of general purpose parallelism very well, and then you have your accelerators, which are really attacking the specialized computation, really getting energy efficiency. But the real challenge in designing these things is figuring out what those accelerators should be. So is there a kind of a process that you guys go through to identify the promising application domain or something, and then figure out what new accelerator would complement your existing set?
Yeah, I think you're absolutely right. The key issue here to continuing Moore's law in terms of performance is to identify the key hardware kernels. Is very interesting work, I know, going on, your own work and Mark Horowitz's group in Stanford in this area. Again, a 70-person company, we can't know everything, so what we have to do is really find the right partners, both academic and industrial partners, to help us identify those kernels. I'd certainly say that for the future, things like deep learning support, and maybe support for 2D FFTs for lens-free microscopy and other applications would be likely candidates. But to be honest, the area is in such flux that the key thing here is being able to react quickly. So essentially, we have a generic drop-in accelerator framework that contains the buffers and contains all the control logic, and you can essentially drop a blob of logic in there, so we can turn things around fairly fast. When we know that the big issue is, can you do that in a time-efficient way when you're trying to tape out a chip that costs a lot of money and where timing closure is difficult to achieve. So I think all of this kind of thing, you have to really start looking at the requirements for your next generation product a long time out, and find, the key really is to find the right partners, whether academic or industrial.
And I think you had some chips that you wanted to.
Gary has them. We can show them. We can show them later on. As
you can
tiny
maybe
BGAs.
see them later. They're quite small and nice. Okay. Well, let's thank the speaker. Okay. Our next talk is by Javed Barkatullah, and it's entitled Goldstrike 1, Cointerra's first generation cryptocurrency processor for Bitcoin mining machines. So for those of you who are kind of new to the Bitcoin mining sphere, this is a really exciting area where there have been a number of kind of an arms race of ASICs have been developed for Bitcoin mining, and Cointerra is one of the has one of the leading implementations. So this will be very exciting. Javed is currently Senior Director of Engineering at Cointerra. He received his Master's and PhD in Electrical and Computer Engineering from the University of Iowa and an MBA from Willamette University in Oregon. Javed has over 23 years of experience in research, design, and development of high-performance microprocessors, SoCs, and custom processors. And he has worked in the past at Intel, NVIDIA, and several technology startups. And I should mention during the Q&A session, we're also going to have Timo up on stage to answer any questions that people have about cryptocurrencies in general.
Thank you, Michael. It's an honor to be here to present our first generation cryptocurrency processor. Before I get started on the design and implementation aspects of the Bitcoin mining ASIC, let me take a couple of minutes to give a little background on what Bitcoin mining is all about. So Bitcoin is, as you know, is a virtual cryptocurrency which you can use to buy or sell real-world goods and services. Like any other financial network, for example, Visa or MasterCard, in order to clear a transaction on the Bitcoin network, the transaction has to be validated and then entered into a ledger. However, unlike a traditional financial network, the ledger is public and the entire system is globally distributed. So any node connected to the Bitcoin network can validate a transaction and enter that transaction into the ledger. The public ledger is the blockchain and consists of blocks. I have got a picture over here. The block contains the block header and a linked list of all the newly validated transactions that are bundled into this block. So in order to win the right to clear a transaction, a node has to solve a mathematical puzzle. So there is a race to solve that puzzle first, and whoever solves it first gets the right to clear the transaction. The computational work consists of finding an integer called the nonce, such that such that if you do the double SHA-256 function on the concatenated message with the nonce, you get a hash result which has target number of leading zeros. SHA-256 is a cryptographic hash function, and like any other cryptographic function, it's a one-way function, meaning that knowing the result, you cannot back-predict what the input was. So like any other one-way function, SHA-256 is best solved using sheer brute force, meaning you have to do exhaustive trial and error search of a very large solution space. Because this process is so compute and time intensive, this type of work benefits from customized hardware. And also, you need to do this using the least amount of power and as fast as possible. For various reasons, the amount of Bitcoin mined on the Bitcoin network is controlled. One reason is logistical, because since the Bitcoin network is a globally distributed network, you need in between each Bitcoin mine, which is each new block is appended to the blockchain, you need to give certain amount of time so that a consensus is reached, which is the next block that should be appended globally. So in order to control the amount of Bitcoin mined, the network difficulty is adjusted for each group of 2016 blocks mined based on the time it took to mine the previous 2016 blocks. The desired mining rate is 1 block every 10 minutes. So 2016 blocks should take exactly 2 weeks to mine. The difficulty of it's controlled by setting the target number of zeros in the result. So if you increase the number of zeros in the target, the difficulty increases, and vice versa. As more and more hashing capacity is getting added to the Bitcoin network, and because we have because there is a control on the amount of Bitcoin that is mined, the Bitcoin difficulty is also increasing. So the graph here, so the graph here shows the graph here shows the hashing capacity on the Bitcoin network, which is shown on the left-hand side axis, and the difficulty on the right-hand axis. And you see there's almost 100% correlation between the capacity and the difficulty. So initially, in January of 2009, when the Bitcoin network started, the difficulty was very low, and you could do the mining using CPU from your laptop or a desktop computer. As the difficulty increased over time, the mining first moved to GPU-based computing platforms, and then to FPGA-based platforms, and finally, around early 2013, it moved to custom ASIC-based platform. Currently, the race is to build the highest performance, yet most power-efficient mining platform based on custom ASICs. Our company, Cointerra, was founded in May 2013 with the goal to build Bitcoin mining hardware with the highest performance and lowest power. Goldstrike 1 is our first Bitcoin mining ASIC processor chip, and this is used in our mining appliance called TerraMiner 4. The RTL development work for the Goldstrike architecture started middle of June of 2013, and we taped out our design on November 19, 2013. During this time, in parallel, the system design for the TerraMiner also started around mid-August. We received our first silicon on December 28, 2013. It was a record 49 days from tape-out to first silicon. And our first system was shipped to customer around mid-January 2014. So this is a record 7 months from design start to full system shipment to customers. So let me now switch gears and actually go into the architecture of the Goldstrike processor. The chip consists of 120 hash engines. Each hash engine is solving a different problem. So at any given instant of time, there are 120 different problems being solved. Each engine explores for a solution over a 32-bit nonce range, and hence requires a new work consisting of 384 bits every 2 to the power 32 clock cycles. So if the processor is running at 1 gigahertz, a new work is needed per core every 4.3 seconds. Because our input rate is so low, we can afford to use a slow speed 4-pin SPI port to transfer data to the ASIC, to our Goldstrike chip. There is a 128 entry deep and 384 bits wide input FIFO, and a 65 bits wide 128 entry output FIFO. Every time a new data is shifted into the input FIFO, the contents of the output FIFO is shifted out. With a simple register addressing scheme, the input data can be written out into a 384-bit pipe control register, PCR for short. With the PCR, we can enable or disable any of the 120 hash engines and also set a specific nonce range over which the engine should be searching for a result. And this is good for test and debug. There is a PLL to synthesize core clock from a 50 megahertz crystal input. The PLL has a bit bang interface through which we can control the PLL. We also have got a thermal diode, and it is used to monitor the die temperature. And from the system level, we can adjust the frequency and supply voltage of the die to control the temperature of the die. Now let's look at one of the hash engines. The input interface transfers or loads a new work from the input FIFO into the hash engine. Each hash engine performs 2 rounds of SHA-256, and the SHA-256 algorithm itself has 64 iterations. So essentially, we have a pipe, both the iteration and the 2 rounds of SHA-256 is fully unrolled, so giving us a 128 entry deep pipeline. This pipeline is divided into 2 parallel pipelines. One is the message pipeline, and one is the compressor pipeline, as shown in the picture. There is a nonce counter that counts from 0 and up to 2 to the 32 minus 1. So at any given instant of time, there are 128 different nonce values being processed in the pipeline. After an initial latency of 128 cycles, a hash output is produced every clock cycle and is checked by a comparator whether that hash meets the target number of zeros, or if the target criteria is met. If the target criteria is met, that result is handed over to the output interface, and the output interface places this result in the output FIFO. So, let's now look at a single stage of the compressor pipeline. Each of the inputs are 32-bit words. Inputs A through H are connected to the previous output of the previous stage. K is a 32-bit stage-specific constant. And W is a 32-bit word that comes from the corresponding stage from the message pipeline. At every stage, new values for the word A and E is computed using this complex math. The remaining, and the result is stored in register A and register E for the new values, and the remaining registers B, C, D are simply a staging register for previous values of A, and registers F, G, and H are staging registers for the previous values of E. So now let's look at the message block, one stage of a message pipeline. The input is 512 bits word divided into 32-bit wide words W0 through W15. Here also, at every stage, a new value of W15 is generated based on W0, W1, W9, and W14. The new value is stored in the W15 registers, and the registers W14 through W0 are essentially staging the 14 previous value or 15 previous values of W15. Here is the die photo of our design. We taped out on GlobalFoundries Hanke metal gate 28 nanometer process with 9 metal layers. As you can see in this picture, it's a 11 by 11 grid. The center grid is the top level, the entire top level logic, And the remaining 128 grids in this picture represents a single, each of those 120 grid boxes represents a single hash engine. In between the hash engines, there are routing channels to route all the control and data signals. All the input and outputs are on one edge of the die. So we package this die into a 37.5 millimeter by 37.5 millimeter full flip chip BGA package with 4 bare dies. At 0.7 volt and 1.05 gigahertz, each die can deliver 125 gigahertz. Each die can deliver 125 gigahashes per second and consumes about 125 watts of power. So the package can deliver 500 gigahashes per second at 1.05 gigahertz and 0.7 volt, consuming about 500 watts of power. When designing at the system level, we explored different cooling options. And there were some of the cooling options were heat sink with forced airflow, which is common in CPU applications, liquid cooling, which is more popular with gamers and overclockers, and immersion cooling, which will work more efficiently for data centers. Because we wanted a common solution for individual consumers as well as data center, and we also wanted to minimize our development cost. We chose the liquid cooling solution for our system. The picture here shows the simulated temperature gradient for a dual package system board we are using in our TerraMiner system. So here is a picture of our TerraMiner appliance. Each TerraMiner appliance consists of 2 of our boards, so total 4 packages delivering 2 terahash per second hash rate. The packages are, that picture shows the cooling heads attached to our Goldstrike package, which circulates antifreeze as a coolant. We have a 4U chassis and it is chosen so that it can accommodate our radiator cross-section and the fan size that balances cost, performance, and noise. Here is another picture of our TerraMiner appliance. 2 fans in the front pulls air in, and 3 fans in the back is pushing air out through the radiator. And one thing to note is that the thick car battery cables that is delivering 84 amps of current to each board at 12 volts. So here is a picture of our TerraMiner in a data center deployment. We have over 5,000 TerraMiners deployed already, and the numbers is increasing rapidly. And currently, our TerraMiner represents almost 4% of the entire capacity of the Bitcoin network. Some of the challenges that we faced, besides the challenge of a very short schedule from RTL start to design tape out, and the pressure to ensure a fully functional first silicon, The other challenges are the high node toggle rates, high power density, and high sequential to combinational ratio. The SHA-256 algorithm results in very high toggle rates. Toggle rates over 80% is common on all our data paths. And because of this high toggle rate, it results in very high power density, and cooling and delivering power to the die and cooling was a challenge. However, the design choices we made mitigated those problems. And the problem was that because of the high sequential count compared to combinational, we have to distribute clock to all those sequential cells and also ensure a quality clock to all the cells. So that was also a challenge, and it took several iterations to close timing. One thing that worked in our favor was that the design was naturally the design naturally provided a high degree of repeat and reuse. Within the hash engine, we have the same or similar stages repeated 128 times, and then at the die level, the same hash engine is repeated 120 times. So optimizing the common core block paid off big time. Also, we have in-house engineers with 25+ years of experience, and that experience was complemented by the design implementation team from Open Silicon. All in all our efforts paid off, and we got a fully functional first silicon in a record amount of time. There is a continued race to build and deploy the most cost-effective Bitcoin miners. We are working on designing new products and solutions that will maintain Cointerra's leadership role in the Bitcoin mining industry. Thank you very much for your attention, and I'm now open for questions. And I also have Timo here too.
Great. Question over here.
David Cantor. What was your TJ target for the, you cited at 0.7 volts, 1.05 gigahertz. What was the junction temperature?
85 degrees.
Thanks.
Yeah, Bill Rash, Intel. I wanted to ask about alternate applications of the hardware. Since it searches for inputs into the SHA-256 function that match an output, could you use it to try to decrypt data that's been encrypted with SHA-256?
No, you can actually not, because is the microphone working? Okay. Now, the nature of the chip and the nature of the problem is that it's so highly parallelized that we produce so many outputs that you could never get them out of the chip. So if you want to use it for other searches, you have to build a proper comparator into the chip itself. And our chip does only the particular search that is needed for Bitcoin. So there's no other application really possible except for Bitcoin mining. Another reason is that the messages that are being processed are very special for the Bitcoin application. And the pipeline is so highly specialized that it only processes these kind of messages. And you cannot use it to actually compute the hash of arbitrary messages.
Okay, thank you.
I don't think you had enough information. I don't have enough background to do the calculation, but was wondering how many kilowatt hours would be required to solve a typical iteration to find have a mining success. In other words, how many machines would you need to have a high probability of finding current number of leading zeros, and how would that all calculate out to kilowatt hours?
Okay, I don't have the number in kilowatt hours in my head, but just to give you some ballpark figures, the current network difficulty is such that you are looking for about 65, I think, leading zeros. So that's quite an impressive space that you have to search, to brute force. And actually the probability of solving it is so low that if you take a single one of our machines, you're not guaranteed that over the lifetime of the machine you will actually solve this problem with
Okay,
one
so that's
single machine.
but the more interesting question is, how many of your machines do you have to have some probability of solving it in 10 minutes?
Yeah, the more the better, right? The
Obviously.
probability is proportional.
But
So-
presumably it's not interesting to buy the machine unless you can afford a number of machines that give you a real probability of finding some of these.
Yes, but so there's actually a mechanism that Bitcoin miners use to circumvent this problem. They they collaborate in so-called mining pools, and they share their computing power, and they measure how much computing power each member has contributed, and then they share the revenue as well. So if you're a small miner, let's say you don't have 1,000 machines, I think 1,000 machines
Right.
may be
I
a
won't,
number.
I won't hog the time, but just to finish that, that's good news. That means we're not all wasting, to the extent that there's only a small number of big collaborations, we're not wasting huge amounts of money all racing for the same thing, but rather collaborating. But we can still answer the question of how many kilowatt hours are we burning on on finding Bitcoins?
Yes, so I think the overall network, if you're assuming 1 watt per gigahash, at the moment consumes about 150 megawatts worldwide. And that's 3,600 Bitcoins a day. So if you divide that, then you get a number what you need per Bitcoin.
Chris Rowan of Cadence Design Systems. I don't follow this field closely, but there is the emergence of rival virtual currencies which use apparently other hash functions in order to do the computation. What is the pressure for more versatility as well as more energy efficiency in order to create coin mining operations that may transcend the market for Bitcoins?
Yeah, the different mining algorithms or different hash functions are certainly out there. People have experimented a lot with them and have designed all kinds of alternative coins to Bitcoin that use them. One reason for them was actually when ASICs came around for the SHA mining, that people liked mining on their GPUs so much that they were looking for an algorithm that was kind of resistant against designing an ASIC, so that an ASIC would have less of an advantage over a GPU, say. And they came up with the script algorithm to use for that. But now we have reached a point where ASICs already exist for the script algorithm as well, and this advantage has kind of disappeared. Other than that, I think this is more of a playground. People experiment with everything. There's certainly a strong network effect favoring a single currency, a single virtual currency instead of many. Even though the many will still exist because people like to experiment, and that's certainly a good thing. If you compare the algorithms, I think SHA is just a perfect fit, because what you want is you want the problem to be difficult to solve, but as easy as possible to verify. And using SHA for that is just perfect. Script is just more work to verify.
Generally, Huawei Technology. Really quick question. How big is your design team, please? How many people here?
What was the question?
Sorry, how many people in your design team?
In Cointerra, we're 34, and the engineering team is around 10.
Thank you.
Hi, Charlie Demergent, Semi-Accurate. What's the cost on one of the appliances?
So this appliance sold in the beginning for $6,000, the 2 terahash system, and the current price is $3,000.
So this is touching upon one of your data points that the total power consumption is 150 megawatts, and that gets you about 3,600 Bitcoins a day. So I'm assuming that the exchange rate is higher than that, as in a Bitcoin is worth more than the power you spend on it. But let's say there's some, I'll finish my question.
Yes, correct, correct. The dollar amount for the Bitcoins is higher than the electricity spent. Yes, that's
Sure.
correct.
So let's say there's some catastrophic event and there's zero faith in Bitcoins all of a sudden. Now, typically in the context of a real currency, there's a central bank that steps in and does all kinds of things to prop up the Bitcoin. But if that happens, are you guys going to be the central bank or are you guys toast?
Okay, that's a good question. So Bitcoin is completely decentralized. There's no central authority that can govern anything, that can guarantee either the rate of issuance of new Bitcoins or that can guarantee an exchange rate or anything. It's not possible. Everything is pre-programmed in the algorithm, coded, hard-coded in the open source code that everybody who participates in the network has agreed to, and it is practically not possible to change any of these parameters.
Thanks.
So it looks like we're looping around on the question askers. So I will ask my question, and then that will be the last question. These guys will be down here. So I'm a bit of a Bitcoin mining fanatic, and I like Bitcoin mining ASICs and own some. So I'm going to ask a technical question about your implementation.
Okay.
So as you noted, you have like this 80% transition rate. And if you think about Bitcoin mining, it's actually like the worst case for dark silicon. It's like pure combinational logic, not much RAMs on there, toggling, stuff like that.
Zero RAM.
Yeah, 0 RAM. So this is like the worst case for power density. So in the implementations I've seen in Bitcoin mining chips, there's kind of like two that have emerged. So one of them is the pipeline implementation like you guys have, and that's probably most of the Bitcoin mining chips I've seen. But there is one other implementation, which is more of a mining in place kind of approach, like the Bitfury machine, which is sort of focusing on reducing all that pipelining as much as one can. And so I guess I was wondering, in the context of this power density challenge of Bitcoin mining, where Bitcoin mining is really pushing the envelope of power density for chips, what kind of architectural changes do you see in future generations? Like what are the kind of architectural techniques that are going to come out to try to improve this for future technology Bitcoin miners?
So as you touched on it, the biggest issue here is to reduce the power density and reduce the toggle count. And so all our efforts in the next generation is trying to do things that will reduce that. And some of those are proprietary information, secret source. I cannot reveal it here, but all I can say is that we are working very hard to reduce the power. So basically, our metric is milliwatts per gigahash per second, and we are trying very hard to reduce that number.
Let's thank the speaker. Okay. So our next talk is entitled RayChip, Real-Time Ray Tracing Chip for Embedded Applications. The speaker is Hee-Jin Shin. Hee-Jin is the Chief Strategy Officer and Director of Business Development at SiliconArts. Before joining SiliconArts, he worked at a technology-focused private equity firm in technology investment banking arena. Prior to his investment experience, he also spent his time developing digital appliance products at LG Electronics. He graduated from Yonsei University with a major in computer science and earned an MBA from Kellogg School of Management.
Hello, everyone. My name is Hee-Jin Shin, and I'm a Chief Strategy Officer of SiliconArts. Today, I would like to thank each one of you for taking the time for my presentation on RayChip, which is the world's first commercialized real-time ray tracing chip for embedded applications. I would like to start off with a couple of introductory slides on graphics algorithms and ray tracing technology, and further dive into our main topic, RayChip. Ray tracing, in computer graphics, there are two types of ray tracing methodologies, rendering methodologies. One is rasterization, which is dominantly used in today's mainstream GPU in mobile, embedded, and PC systems. The other is ray tracing. Ray tracing is a classic rendering algorithm for photorealistic rendering. So far, it has been widely used for offline rendering, but has been regarded as the next generation graphics algorithm that is expected to replace existing rasterization in the next several years. RayChip is the world's first real-time ray tracing chip that can be applied in commercial embedded systems. This chip enables real-time ray tracing, which results in implementing reality-like 3D graphics in games, UI, and several other applications in today's TVs, set-top boxes, and game consoles. It also has a diverse set of functionalities and easy-to-use software API for content developers. Yeah, actually, that's got it. Ray tracing generates an image by tracing the path of light through pixels in an image plane and simulates the effects of its encounters with virtual objects. There are several advantages of ray tracing algorithm in computer graphics. First, ray tracing supports global illumination effects such as reflection, refraction, transmission, and shadow. And this leads to photorealistic rendering of 3D graphic image. Second, ray tracing supports can deal with decorative scene implementation, which specifies how a scene should look like without specifying how this effect should be achieved. This means that scene description can be rendered fully automatically without the help of creating applications. However, there are also several disadvantages of real-time ray tracing algorithm. First, ray tracing requires a tremendous amount of computing power, especially related to its traversal and intersection test process. Second, there are critical problems relating to dynamic scene support and to recursive loops that complicates the stream processing. All of these problems have been solved in RayChip architecture, as details will follow in the next slides. Now, rasterization pipeline maintains simple stream process by projecting each triangle to the 2D screen. Whereas for ray tracing, this pipeline contains recursive loops, which are the key to its ability to compute global information in the scene, but it requires huge amount of hardware resources for computations, and it is even harder to implement into small silicon of real-time applications. From content creation point of view, ray tracing provides easy-to-create environment for developers. This figure shows the content development process of ray tracing algorithm. Ray tracing automatically simulates the effect of lights, but rasterization requires various kinds of maps, such as environment map, shadow map, reflection map, to overcome the lack of reality in 3D contents. Additionally, shader programming effort is required. So ray tracing helps under-trained designers and developers to have easier access to developing 3D contents, and this leads to saving time and money. Okay, let's go to the point. In the next slides, I will introduce the overall hardware architecture of RayChip and our design decisions. We have made several important contributions in achieving real-time ray tracing, and facilitating convenient development environment. First, RayCore, a ray tracing hardware unit, is a fully hardwired logic that is designed based on BIMD parallel architecture. It also processes multiple ray bounces recursively to create realistic images. Second, RayTree. It is an acceleration structure building hardware unit which has been added to meet the high performance requirement for per frame acceleration structure building. Lastly, easy to use API allows developers to create high quality 3D graphics applications at lower cost. Now, this block diagram illustrates the overall RayChip hardware architecture. RayChip consists of 6 ray cores and 1 ray tree. As you can see from the floor plan, these 2 key components occupy a significant portion of the silicon area. Later, I will explain each component in detail. In addition, there are various types of components, such as ARM11 CPU, 2D engine, HDMI 1.3, USB 2.0, and other peripherals. So here is RayChip's actual silicon image and die shot. RayChip SG141F is fabricated based on Fujitsu 55 nanometer low power process technology. Its die area is 9.6 by 9.4 square millimeters. Among important components, 6-core RayCore GPU has 30 million gig counts and has maximum benchmark performance of 100 mega rays per second when operating at 266 megahertz. This hardware sufficiently delivers real-time ray tracing performance at high definition, 30 frames. RayTree is comprised of 1 scan tree and 2 KD tree units. It has 3.5 mega gig counts and has maximum benchmark performance of 1 million triangles per second at 266 megahertz. RayChip also utilizes 2 DDR3 interfaces for memory management. This slide depicts the detailed process of ray tracing. In the pre-processing stage, 3D graphics data is loaded into the DRAM via SD card, and ARM11 CPU performs scene management. Then, in the acceleration structure building stage, RayTree builds 3D graphic data into acceleration structure called KD tree for efficient ray tracing implementations. A KD tree is a space partitioning data structure for organizing points in a k-dimensional space. So static 3D graphic data is built just once in the beginning of the scene, but dynamic moving 3D graphic data is rebuilt on every frame. RayCore then handles the entire process of ray tracing pipeline. Ray is generated, traversed, and then intersected to determine whether it produces reflection, refraction, or shadow. After proceeding through recursive ray bounces, shading and texture mapping processes take place to color the pixel. In the post-processing stage, 2D engine performs operations such as biplit, scaling, PIP, and then final rendered image is delivered to the display processor. So RayChip contains all of these above-mentioned hardware blocks that are needed to implement real-time ray tracing. RayChip is designed to achieve high performance and high scalability based on tile scheduling. Based on this mechanism, each RAY core GPU renders a tile block one at a time. For instance, RAY core number 1 renders tile block number 1, and RAY core number 2 renders tile block number 2, and so on. Tile scheduling further enhances rendering efficiency by dynamically allocating a RAY core into certain tile block. For instance, when one of RAY cores is in ideal mode after finishing its predetermined task, the tile scheduler allocates the next tile to this RAY core. From software perspective, we also provide RAY core API for easy programming. This ray tracing API provides similar interfaces to OpenGL ES programming. Complete API specifications and its programming guide are available on SiliconArts website. So here are some examples of RayChip's primarily target applications: TVs, set-top boxes, digital signage, media box, and game consoles. By leveraging the benefits of ray tracing technology, we expect to add values in enhancing the graphic quality of 3D applications in both consumer and commercial segments. From now on, I'm going to talk about design decisions on RayChip, followed by in-depth presentation on its key components, RAY core and RAY tree. Anyone interested in learning more about these two technologies, please refer to the paper to be published in ACM Transactions on Graphics in August 2014, which will also be presented at SIGGRAPH 2014 in Vancouver, Canada. This slide summarizes the main design decisions of RayChip implementation. To realize real-time ray tracing, we applied various novel concepts, such as fixed pipeline architecture, unified traversal and intersection architecture based on MIMD, an efficient memory latency high technique, and a hardware acceleration structure builder. As a result, our work achieves high performance, a small silicon area, and low power consumption. RAY core consists of 5 subunits. A setup processing unit initializes or passes ray information. Then a ray generation unit generates primary and secondary rays. Traversal and intersection units perform both node traversals and ray triangle intersection tests. A hit point calculation then calculates XYZ position of the hit point. Finally, a shading unit performs Phong illumination and texture mapping. We chose MIMD architecture over CMD architecture to achieve high hardware utilization regardless of ray coherency. In order to support MIMD architecture, each pipeline needs dedicated L1 caches. Despite of increased hardware area, MIMD architecture produces better ray tracing performance than CMD architecture. A recent paper published by University of Utah also proves that MIMD architecture is 6 to 10 times more efficient than CMD architecture in realizing real-time ray tracing. The memory management system of the traversal and intersection test unit includes 2 levels of caches. Between L1 and L2 caches and memory controller, there are 2 types of FIFO. Address FIFO handles memory requests, and address data FIFO delivers address and data to the upper level caches. We also propose a simple multi-threading architecture called looping for the next chance. When a cache miss occurs, the ray thread is set to the ideal mode during the remaining stage. In the next loop, the ray thread is reactivated and reaccessed to the cache. The pros of this scheme are ease of hardware implementation, efficient hiding of memory latency, as well as use of existing internal memory. So far, I described Ray Core. Let's go to Ray Tree, which is another next main unit of RayChip. Ray Tree consists of two pipelines types, binning and sorting. A binning-based pipeline is used for making upper-level nodes called scan tree, and sorting-based pipelines are used for making lower-level nodes called KD tree. This approach aims at fast KD tree construction without significant tree quality degradation. For a sorting-based pipeline, we include internal SRAM. All data of the execution structure, build procedure, such as sorting, split plane selection, and geometry classification, are maintained in the SRAM. This approach minimizes off-chip memory accesses. We also propose node scheduling to support burst memory access in Ray Tree. Problems arises on burst success due to depth first order when constructing node information. To solve this problem, our node scheduler reallocates a node construction order. Next, implementation and results will be described. Here are the test benchmarks which are used for RayChip evaluation. The number of primitives ranges from simple scene of 5K primitives to heavy scene of 300K primitives, which are suitable for targeted embedded applications. Ray tracing performance based on the test bench resulted in implementing 100 mega rays per second and producing 30 frames at HD resolution. The performance figures may vary depending on the scene complexity, but our test bench will represent the size and the quality of typical 3D contents that can be found in today's embedded systems. Here are test bench for Ray Tree performance evaluation. The number of dynamic primitive ranges from simple scenes of 1K primitives to heavy scenes of 30K primitives. Ray Tree's KD tree build performance based on this test bench and resulted in implementing 1 million triangles per second. This figure is much superior when compared to latest mobile processor as well as high-performance CPU in PC system. Here are some examples of how RayChip performs in two different settings. The left-hand side image is rendered at ray bounds of 0, and as you can see, there's no light effects. On the other hand, the right-hand side image is rendered at ray bounds of 14, and there is natural light effects depicted on dynamic lake surface. Also, simultaneous expression of reflection and refraction can be realized when background image is changed immediately. Here's another demo called Living Room. The left-hand side image shows bluish opaque table and entire objects without shadows. On the other hand, the right-hand side image shows natural light effects depicted on transmitted table, refracted cup, global shadows for all objects shown in the scene. This is an interesting user interface demo with water drops being the folders for app icon storage. The left-hand side shows gray opaque water drop folders. On the other hand, the right-hand image shows natural refraction image on water drop folders. Lastly, mobile demo. Left-hand image shows no effect of light. On the other hand, the right-hand image shows various kinds of ray tracing effects on rotating mobile, transparent table, transparent window, and so on. All of these lifelike effects are made possible to operate in real time using RayChip. To sum up, RayChip is the world's first commercialized chip targeted to realize real-time ray tracing for embedded applications. RayChip includes real-time ray tracing hardware unit called RayCore and acceleration structure build hardware unit called RayTree. And also, RayCore API allows easy-to-use programming environment for ray tracing. As a future plan, we are focusing on the following topics. First is virtual reality platform. SiliconArts has its proprietary ray tracing hardware technology and has recently developed sound tracing technology. Sound tracing is a technology which stemmed out from ray tracing algorithm, but instead of tracing the light, it traces the sound propagation path and calculates the indices of reflection, refraction, diffusion, and absorptions. The result of two combined technologies is immersive VR system that will be applicable in many of next generation devices. Second is RayChip Series 2000 chip. This second generation ray tracing chip will be equipped with advanced graphics functionalities such as soft shadows, ambient occlusion, displacement mapping, and so on. On top of that, OpenGL ES GPU will be integrated with ray tracing GPU to deliver maximum graphics performance and support traditional graphics contents. Lastly, real-time global illumination. Global illumination is the ultimate graphics technology which implements both direct and indirect lighting. SiliconArts will develop path tracing algorithm and several noise filter techniques to fulfill the needs of photorealistic graphics in the near future embedded systems. Thank you for listening to my presentation. I'm open up for the questions.
I have a question. So can you speak a little bit to the scalability of your design in terms of, to what extent can I just stamp out more of those cores?
Okay. So basically, RayChip is designed with technologies called RayCore and RayTree, and each of these cores is highly scalable. So for instance, if you're targeting the mobile applications, you may require 6 cores of RayCore to meet full HD 30 frames. But if you're targeting console quality, you may require 12 cores of RayCore. So unlike the rasterization and shader GPUs, our architecture allows scalable performance as well as reducing the power at the same time.
John Mash, Chief TechVisor. Thanks for a very interesting talk. And I have just sort of a humorous question is, gee, but we didn't see the Utah teapot. I guess it was too simple.
Oh yeah, teapot is simple, yes. Yeah. That's correct.
Okay. Unfortunately, we have to kind of keep things on schedule, so we're gonna transition to lunch. I'm sorry to cut you off.